So, hi, I'm Connor Colombo, a Carnegie Mellon mechanical engineering and robotics student, and also the head of ground software for the Iris Lunar Rover. Today I'm going to present Driving Off the Edge of Space, building systems to pilot the first private lunar rover. For background, CMU's Iris Lunar Rover will launch in Q4 of this year, and when it lands, it will be the first private, first student built, and first American robot to drive on the moon. For context on what that means, here's the complete history of unmanned lunar rovers, essentially all lunar rovers excluding Apollo. In 1970, the USSR landed Lunokhod-1, about the size of a person, 1,700 pounds, and powered by batteries, solar panels, and plutonium. They then landed a very similar rover in 1973. Fast forward 40 years, and China lands the third rover on the moon, U-2, aboard the Chang'e 3 mission. It's about the size of a child, 310 pounds, but still powered by battery, solar panels, and plutonium. But it didn't live very long, so they then sent U-2-2, essentially a clone of it, in 2019. Later that year, Israel attempts to land a hopping lander, which is sort of quasi-lander, quasi-rover, and it crashes and fails. Later that same year, India attempts to land a lander-rover combo, and it crashes and fails, which means that if we do not crash and fail, we will be the fifth rover on the lunar surface, and we will land a 1-foot toaster-sized rover, which weighs about 5.5 pounds and is powered by effectively 6 flashlight batteries. So I put these power, size, and weight parameters here to contextualize what we're trying to achieve, particularly that is to say how far or how fast we want to drive, and by extension, how much of the lunar surface we hope to cover and survey, which is sort of the purpose of a rover. So over its mission, Lunokhod-1 surveyed 33 meters per day on average, Lunokhod-2, 319, U-2, 8 meters, U-2-2, 0.8 meters, and we're targeting for 127, which means if we succeed, we will be the second fastest unmanned object in lunar history. So this objective is somewhat challenged, though, by our low size, weight, and power. So there are a bunch of reasons to be low size, weight, and power. Every kilogram costs millions of dollars. High-density computing, which would give you lots of computational power, is often challenged by high levels of cosmic radiation that you see on the moon. And every watt of heat you spend computing is an extra mass that you need to dissipate it, as well as extra engineering to engineer that radiator. But this is not without impact. It may sound nice to be low in size, weight, and power, and convenient engineering-wise, but it poses one big challenge. We have extremely limited onboard computing capabilities. Now, we can offset this by offloading much of the perception and sensor data down to Earth. But the problem is, we leave most of our data on the moon. We only have a 50 kilobit per second downlink, which is about 2,500 times less than US broadband, which means we only get one full bit of data every 4.2 minutes. And what we get are 2 compressed 0.3 megapixel images, one from a front camera, one from a rear camera, and about 6 seconds of sampled IMU, so accelerometer and gyroscope data, at about 100 hertz. Now, this might not be a problem. You can think, oh, machine learning, we can just upsample it. No, there is no data set for what we're doing. No one's done what we're doing from our perspective before. You can't train a machine learning algorithm robustly enough to send it into space. We are effectively collecting that data set for future missions, implicitly by doing this. So the whole crux of the challenge for this Earthbound software is that Iris is an eye on the moon, but its brain is on Earth. And that brain is ground software. Our objective is to teleoperate the rover from Earth so they can carry out the mission, and in doing so, extract as much meaningful information from the little data we get from the moon as possible. Then we have to display that information in the most efficient and intelligible way to the users, and we have to verify that the system will provably work when it's on the moon before we get there, and use the system to train operators before launch. This is important because every 4.2 minutes we get data, as I said before, and by that turnaround time, the operators have to be ready with the next safe move. This is important not only because for a $3 million 48-hour mission, every minute costs $1,000, but also if we wait too long to make a move, we'll freeze in the shadows, or if we're in the sun, we'll bake on the regolith. This is complicated by the fact that not only do we have little data, but from our camera's shallow perspective, shadows and craters are often indistinguishable. Here's a simulated image of the same size and quality we will expect during mission, and as you can see, it's fairly difficult to tell what's actually going on in this terrain. Now you may think, oh, this image is so small. No, actually that's just the size of the image we get. I mean, we'll increase the size, but that's the number of pixels. So I'll first talk about my role as the manager of the ground software team, or as the head. Obviously, I manage the direction of the project, and I serve as the go-between between all the sub-teams you see on the left, as well as between all the other IRIS teams, mechanical, flight software, etc. In this role, I've obviously had to hire and manage personnel. I've had up to 30 at one time, and about 50 in total. Now, I want them to focus on things that are important that they find interesting, so I will often take anything they deem as boring infrastructure. This has led to me being the sole developer for the high reliability backend, which connects the operator's interface to the software stack, and then to the lander, and then to the rover, and back again. This also has led to me managing the hardware, which embodies this software, which are two of those servers you see on the left. In addition, I'm in charge of all systems level documentation, as well as running data and software for all critical systems tests. On the left here, you see the aforementioned high reliability backend, collecting and monitoring data for the IRIS Lunar Rover's thermal vacuum test. In addition, I'm often found creating initial prototypes, or have over the past few years, for various subsystems. So before we bring on a team to actually build it out, I will create the first few iterations to prove if it's a viable concept through testing in what we call paper missions. As a whole, the ground software team is set into 3 different categories. As I mentioned, our objectives are to get data, extract as much meaningful information as possible, and present that data efficiently to the user. So we have the back end, which gets the data, localization, which extracts meaningful information, simulation, which really generates it when we don't have access to a moon to test on, and the front-end UI development and design teams, which present that efficiently to the user. In fact, our design team was the biggest team of all of IRIS for a while because this is such an important task. The first component that they designed, the IRIS terminal, you see here. Now, it's made of many sections. The simplest, of course, is the command line. You send commands, and you can track their progress through the data pipeline. The next is the image viewer. Now, it's used not just to view images, but also to use planar homography to assess the approximate distance to objects on the same plane as the rover, and to display point cloud segmented data on the overlaid on top of an image, so operators can select points of interest that are either visually or locationally useful scientifically, or conversely are hazards, and those can then be displayed on the map. The map is a high-level view of the environment, and it allows operators to simply plan routes given the rover's localized position, and then send those routes automatically to the command line. They won't be automatically sent, but they'll be automatically shown in the command line so operators can choose to enter them. It would not be safe to automatically fill them. Next are telemetry and error analysis. Telemetry is shown simply as streams of data, that's all it is. But error analysis shows not only automatically flight errors, but allows operators to select regions of telemetry that seem suspicious and flag them, and then if we see a bunch of these events happening, we can conclude that something is probably going wrong. And this allows a bunch of operators to do this all at once so that we can have this data going simultaneously. In addition, we have a failure tree. This shows essentially suspicious bits of telemetry or observations, what their root causes might be, and then what the suggested failure resolution modes are. Resolutions are to those failure modes. Lastly, we have an environmental view. This uses structure from motion reconstructed environment maps and displays them to the user as a 3D model that they can then pan around. These are constructed solely from images, and this you see actually comes simply from a simulator. And it's a decent reconstruction of the critical parts of the environment, namely nearby boulders. This then connects to the backend, or OSIRIS, operations server for IRIS. This links all the terminals to a database that is power and data redundant, as well as a backend that's power and data redundant. The terminals where the operators are isn't guaranteed, but power and data are guaranteed mostly for the database and backend. The backend then connects all of the pipeline to the rover. This connection happens through a bunch of steps, from IRIS to our launch provider, Astrobotic, to the Deep Space Network, to lander on the moon, and then finally over Wi-Fi to the rover, and back again. During all this process, the data gets wrapped in a bunch of different ways, and the backend has to be able to essentially unpack it. We can then embody all this in Hermes, the Hollow Earth Restricted Message Exchange System. This allows us to take that entire pipeline and simulate it in one box that is offline, so if we need to test the rover, say, in a field somewhere with no internet access, we can have an accurate test, but remote. Once we have the data, we pass it to ascertain the location of surroundings, or ATLAS. This is our localization and mapping system. It determines where the rover is in an environment, builds a map of the environment, segments that environment, and then labels the segmented bits. And does all this without machine learning. Now, I'm not actually going to dive into these pieces because you've already seen the results in the IRIS terminal with the environment, the 3D environment map, the segmented objects, and the point cloud object segmentation in the imager. But the Atlas Localizer is pretty much useless without access to lunar-like data. So we have a real-time environment and mission interface simulator, or Artemis. This started out as a basic lunar terrain simulator, which was developed by myself in high school a couple years ago, but it quickly developed last summer into a more sophisticated telemetry simulation to simulate stuff for our VIO SLAM system, as with improved photorealism, not only for operators, but so we can have accurate images for the localizer. Then we lastly improved it with a version 3 where we brought on someone with significant game development experience to produce what we affectionately call Moon Minecraft. It uses pseudo-random procedural terrain generation around the rover, much like in Minecraft, to generate the terrain as the rover moves, but not in only a seemingly random way, but that randomness can be guided by statistical data on the spatial density of rocks and craters gathered from NASA's Lunar Reconnaissance Orbiter about our landing site. We've also added advanced telemetry simulation and photorealism designed to match the quality of images we have from the Chang'e missions. Now, this entire stack is useless unless we know it can work usefully on the moon. Problem is we don't have access to the moon, so we conduct what we call paper missions. They used to actually be done with paper, but now they still serve the same purpose, but with our actual tech stack. In essence, we trial new features on these paper missions and see how they affect our primary metrics, namely the nominal decision time and speed made good, or average speed throughout the surface. This mission style will also be later used to select and train operators, which will be the future work of ground software after our upcoming payload acceptance review this month. The key results are that over our months and months of weekly paper missions, we've seen a nominal decision time of 64 seconds, a mean anomalous decision time when things go wrong of 430 seconds, and a typical decision time, assuming 2 anomalous events per hour, of 84 seconds. Critically, these are all considerably less than that 4-minute turnaround time I talked about before. This allows us to then also perform sensitivity analysis to determine how the parameters we can control during mission affect our speed made good. So if we need to make changes on the fly, we can choose which are the most important knobs to turn. The net result is this. As a result of all of our weekly paper missions, we can expect a speed made good of 36.7 meters per Earth day, optimistically going up to 126.4, but even if everything goes wrong, we can still expect to exceed 5.5, which means in the worst case, we're the 3rd fastest object in lunar history, unmanned, and in the expected case, we're the only second to Lunokhod number 2, which in this case would be a success not only for ground software, but for all of IRIS. Thank you. Any questions?
That's a really great talk, Connor.
Thank you. I'm sorry I went a little over on time, but I'm glad you liked it.
No, that's totally fine. And I just had one question, and I think this is because I really enjoyed your talk and also your executive summary, and that would be like looking ahead.
Yeah.
If you're offloading the sensor analysis and planning tasks to systems on Earth,
yeah,
how would this translate to, for example, missions to targets farther than the moon?
That's very interesting. The moon is a very unique target in this case. It would almost only be applicable to the moon and maybe nearby targets like Eros. When you go further, light delay to the moon is only about 4 seconds. On Mars, both communication window and light delay mean you have to wait 12 minutes for communication, but you also only get a communication window once every Earth day. So really the way Mars missions work is they just downlink a whole set of telemetry and it has to operate semi-autonomously, but it does so extremely slowly.
Yeah. Are there any ways that you can think of to get around this limitation?
Well, honestly, we're kind of an interesting crossroads. This is probably one of the few missions that will be conducted this way. I think the way around it is to take humans out of the loop. And our successor mission, Moon Ranger, attempts to do machine learning on the moon using data collected from us and other missions. It's much riskier. They're obviously using a GPU, which can, as I say, can get affected by cosmic rays. But if that proves to work, which it's, again, very risky, but if it does work, it will prove out the case that you can be fully autonomous without humans in the loop on another planetary body, which will kind of change the way these missions are done. This would probably only continue to be done for really low budget operate in the loop missions.
Great. And I know we have a couple minutes left, so I want to open it up to the audience for questions. Sure. Or
Cool. Yeah, thanks.
go for it.
So yeah, thank you for the wonderful talk, Connor.
Thank you.
It's a really unusual experience as an undergrad to build a team of dozens of folks, right? And so I think I have two questions. One is, you're limited by how many people you have access to. In an ideal world, would the team have been bigger, and how would you have dealt with that? Like, how big should the team be to tackle these problems? And then the other question is just like, how do these insights, inform your approach to the rest of your career?
Thank you. Yeah, it's both very good questions. I would say the team size is interesting. I think in some ways, some of the teams should have been smaller. Others would have been nice to have more people. The kind of limiting factor is not only do we have limited access to students, but we have access to students, and they all have, they have other things going on. So one of the big challenges was figuring out how to manage a team where everyone had varying levels of commitment, and that commitment level varied throughout time. And often everyone would get swarmed with, say, exams all at once. So there definitely would have been different team sizes. Though interestingly, near the end, we changed our ask strategy, and before we're saying, oh, we'll take anyone, but then we got a little more necessary to take high talented people. And so we said, masters only, we're looking for really experienced space people. And we actually got more applicants, and they were all considerably more qualified. And we even got PhDs who were CMU grads from years ago. And that completely changed the dynamic, because they're not students. They were just working volunteer considerable amounts of time. I guess the impact, to answer the second question, the impact that had on, I guess, my future career is just that I am fairly entrepreneurial. I hope to go into running a startup, etc. And the experience of trying to find how to not only get people but keep them interested in their work, and then sort of drive a team around a common goal, I think is something I will carry with me for the rest of my career.
Thanks.
Thank you.
No, so Connor, my question is, what is the underlying goal of the mission? Is it just data acquisition, or for future missions, or are you looking for something?
Yeah, so it's interesting. We do have a science team, science sub team. They've partnered with a couple other universities to do analysis of the data. It's varied throughout time. Our base objective is just go there and don't die. The shortest record is for surviving on the moon is 4 seconds. If we survive 5 seconds, it's at least a success. But beyond that, our primary sensor is a camera. We want to collect a lot of data from this perspective and pair it with IMU data, which is, there's a lot of data from Chang'e, but it doesn't have IMU data associated with it, so it's sort of almost useless for training localizers. But this can be useful for lots of subsequent missions. Additionally, we at one point were involved with the NASA SBIR, which was to assess blast ejecta. So essentially, when you land, you spew out a bunch of really sharp particles from the lander. And you want to understand how far those spray, because if you try landing something near, say, an inflatable habitat in a decade, you don't want to burst the habitat. But you also don't want to land so far away you have to lug stuff a very far distance. So we are sort of nominally going to collect that data. It's called BRDF, bidirectional reflectance distribution. It just involves essentially circumnavigating rocks. So if you actually see our map, that's a very key part of the process, is these circumnavigation objects where they have these little arrows pointing to indicate where to take images, and the operators have to plan at least 180 degrees of circumnavigation around the object to be able to then post-calculate BRDF. And then that allows the science team to determine the blast ejecta quantity.
In other words, the operators are not just avoiding problems; they're also guiding the rover to look at the interesting things.
Yeah.
All right. Since we've asked, the 5 minutes for quick Q&A has already passed. We'll be moving into 5 minutes of feedback.
Thank you.
Actually, the breakout room is closing in 1 minute, and we're going to be switching out soon. But I just want to say, Connor, that was a great presentation, and your project is really interesting, and I think Bex has something, or what's your end?
I just wanted to say, I think like, you were attempting to communicate probably far more than should be communicated in 10 minutes. So you spoke really fast. And I think like you lose your audience if you tell them everything but because it's just too much. But at the same time, like your presentation of the Atlas localization and mapping flowchart was perfect, right? You explained the what and the why. And really, I don't know that you did a wonderful job throughout. I just, in general, slowing down and saying less would have been more.
Yes, I definitely agree with that.
Thank you. I especially appreciate the feedback on Atlas. I was unsure about that technique. Thank you.
Great, and I think then that concludes this breakout room.
Thanks.